So we will talk about linear momentum conservation. Now we know Newton's second law. Newton's second law is if net external force is proportional to rate of change of momentum, ddt of p, or you can say delta p over delta t, right? We call it rate of change of momentum. This momentum is a vector, but I will take the magnitude part only. That would be m times v. V is the velocity, m is the mass, right? So mass, velocity. Now if you're thinking about this here, f external, so we will have the equal sign, and the constant is 1. It's famous Newton's second law of motion. So that would be dp over dt, right? So this should be ddt of m times v, or you can say delta mv divided by delta t, right? So here we will consider m to be a constant value. So if m is a constant value, you can take that out. So this is delta v divided by delta t, and that is f external force. Now we will expand v, and that would be m, you can say v final minus v initial, and that would be delta v divided by delta t. Okay, now what we can do, we can individually multiply by m. So m times vf minus m times vi divided by delta t, and that would be f external. Now from here we can do many things. First of all, we will multiply f external with delta t. It's cross multiplication, so that would be f external times delta t is equal to mvf minus mvi. So this is nothing but mvf, so this bit is nothing but momentum, final momentum. This bit is nothing but initial momentum. So this is what is important. Now in physics, net for external force times delta t is called impulse I. Okay, so obviously this delta t is a very small value, so it is called impulse. So in other words, impulse is nothing but change of momentum. Okay, change of momentum. Now if f external force is 0, that means in absence of an external force, what will happen? So the left hand side would be 0, p final minus p initial is equal to 0, right? So from here you can say p final is equal to p initial. That means linear momentum final is equal to linear momentum initial. This is called linear momentum conservation. Linear momentum is conserved. Initial momentum is equal to final momentum. So this is linear momentum conservation. Now we have to understand and remember, this is valid if f external is 0 only, or if not, net force is 0 only. In absence of an external force, linear momentum conservation holds true. So now we will discuss an example, a small example. Consider there is an object m1 has velocity v, and m2 has 0 velocity. Then suppose this is u. Then they are going to collide each other, right? After the collision, m1 has v1 velocity and m2 has v2 velocity. Now this is our initial situation, this is our final situation, right? So there is a situation in between. We don't need that, because if you want to use linear momentum conservation, you need to have the initial and the final situations. You don't have to know about the know about what is happening in between. So this is initial, this is final. Now individually we will look into the momentums. So the momentum of this one P1 would be M1V, the momentum of this one P2, that would be M2 0, right, which is 0. So similarly here the momentum would be P1 final. So this is initial and initial. P1 final would be M1 V1, and P2 final, that would be M2 V2. Okay, so the total initial momentum P total initial momentum, that would be M1 V. From here P total final momentum, that would be M1 V1 plus M2 V2, right? So now you can see in this process, you don't see any external force acting on this system. So F net force or external force is 0 here. So that implies you can use momentum conservation. So using linear momentum conservation, one can say P initial is equal to P final. So P initial value would be M1V is equal to P final value would be M1V1 plus M2V2, and this is the relation that you obtain from the linear momentum conservation.